Let us see magnetism. Okay. Magnetism, if you have, this is I guess chapter 4, right? Chapter 4 for your syllabus, magnetism. Okay. We will not finish the magnetism all of it today. So magnet you are familiar with. Okay, I will give you some very simple pictorial representation. Magnet is basically, magnet is everywhere. Okay, how it is? It is really up to the universe also. It's what all we see is magnet. Okay, what is magnet? Anything, I think the simple definition is, or how the magnet is created. Anything that has a rotation, moment, or some rotational behavior, it can create some field around it. See, electron, proton, neutron, every object that can rotate can create some sort of field. That is what I will come into. I think magnet is everywhere. You can trace back to the origin of life. Okay. Now, what is next? Okay, you can basically from universe to your atom level, if you go, all of them are having some sort of spinning behavior. Okay, two types of spinnings are possible. One is, as you know, one is rotating around its own axis, and another is orbital. Rotating, that's how the sun rotates, that's how the earth rotates, that's how the moon rotates. So it rotates around its own axis, that is the spin component. It rotates around the orbital, that is the orbital component. And the total, these are two vectors basically. You do the vector addition, you get the net magnetic moment. Okay, we will come to that. That's what is this chapter about. But to speak you very clearly, the unpaired electrons are the one which causes most of the magnetic, which induces the magnetic properties into the molecule. So not only the bigger thing like earth, sun, moon, we see the magnetic behavior due to their spinning behavior or rotating behavior. As small as the molecule, even you can go further in, as I think we are trying to discuss the complex. Complex means metal complex, metal ligand is there, metal d orbitals are there. Those d orbital electrons are the one which are essentially giving us the magnetic behavior in different application what we are using nowadays. Different whatever electronic devices, even for our this ATM card, to wherever you see that anything has to do with the unpaired electron, those are coming from the metal complexes. Okay, let me get into. So we will discuss the magnetism of the metal complexes and then get into the lanthanide actinides or lanthanides specifically, and then stop. Okay. So I think I was discussing a moment ago, paired and unpaired electron pairs. Unpaired electron pairs are the one which will be giving this magnetic behavior, because paired electrons will be cancelling out each other. Spinning of electron, as you can see, spinning of electron, and this is the pairing of electron. So spinning the what's that called? Unpaired electron will be giving you the magnetic behavior. Paired electron will cancel each other out. Okay. Now, can you see this behavior? Can you, just from simple experiment, can you determine the magnetic behavior of any compound, such as oxygen, nitrogen? Oxygen is a gas, nitrogen is a gas. Are they paramagnetic or diamagnetic? Sorry? Yes, how will you do this experiment? Simply what you usually do, you cool it down. If you take even nitrogen gas, liquid nitrogen you have heard of, liquid nitrogen big tank goes on and lot of funny experiments can be done. If you liquefy the nitrogen gas, it becomes liquid nitrogen. Now that liquid nitrogen we want to see whether that nitrogen is going to be diamagnetic or paramagnetic. Simply if you take a magnet, this is a magnet, okay, it's a big magnet, and you pour liquid nitrogen through it, you will see that, magnet opposite direction should attract each other, you will see there is no attraction. So this is what a simple experiment can tell you, that liquid nitrogen is going to be diamagnetic in nature. Same thing you do with oxygen, as you were correctly saying that it is paramagnetic. You can do the experiment, you see it is sticking to the magnet. That's the simplest one of the experiment you can do, which can show you what the molecule is made of. Oxygen, nitrogen, it's amazing actually if you think very simply, but do not try to liquefy oxygen, it can be bad, okay. Don't do this, it could be a lot of bad things can happen afterwards if you do not know how to handle it, okay. Right? Of course, there are a lot of other things you see, magnetic levitation, like suspension. You see the magic, P.C. Sarkar or whoever big magician you know of. You see they are showing sometimes, you see this movie, one of the Hollywood movie, what was that? Prestige, I like that. Okay. See, sometimes body is floating, right? You know that, of course, if you look at the movie, if you go to the movie theater or in, of course, you can watch today, tonight if you want, there is some science behind it. So you can make some object as big as like someone like us, a human being float in air. Sometimes that also, of course, can give you the thought. Sometime in the ancient history, Indian history, we see that people are walking on the water. I don't know whether other supernatural things are there or some extra thing are there, but something like this you can explain, perhaps scientifically as well, that there is opportunity for science to contribute. I don't know, I don't want to caught into some sort of controversy here. So something can be floated. You can float something like, I think movie is not working, even what is this fruit? Strawberry, yeah, I love it. So strawberry can be floated, right? Well, of course, this is interesting, a magnet, right? Otherwise, I think magnetochemistry, if you are to discuss, you have to understand electron spin. See, this is little bit physics in there. I will try to skip it because you have studied it already. It's all, we will show you the equations. So an electron has two intrinsic spin states, which are referred as up and down or alpha and beta spin. Okay, alpha and beta spin. Electron orbital motion is nothing but what you see in the universe. Center is nucleus and electron is spinning. Okay. Now, nuclear spin, of course, some nuclears are also having spin. You just read. Okay, it becomes a little bit boring to teach because you know it. Okay. Now, magnetism. This is an equation. What we are trying to say? We have a magnetic field. You put an object into the magnetic field. A molecule, d orbital containing d orbital, or any non-magnetic molecule, whatever net effect, it could be a non-magnetic, any molecule you can put, any object, you put this one. Okay. The net magnetic behavior or magnetism you are going to get is the magnetic field plus whatever it can induce on it. The magnetic field can induce some magnetic behavior inside it or in it. So this is what the equation is. The magnetic field what gets generated or total magnetic field you get is equal to the applied magnetic field H and the intensity of magnetization, how much magnetization it is going to have, or how much hypnotized or magnetized it is going to get. That's the total magnetic field within the substance. What's the field? Not only the field you create, what's the material made of, that makes a difference. The type of material you have, that makes a difference. Okay. All of you are in IIT, all of you are attending the same class. Some of you will be millionaire, trillionaire, and you will give me some money. I will be very happy, right? Donate profusely. When you are donating, ji khol ke donate karo. Okay, give back to IIT. Okay, really, I mean, we need money, a lot of money. A lot of you will be having, I'm sure, startup companies. Some of them will be bought out by some established company. You will be filthy rich. You have no idea what to do afterwards. Just think about me, okay, for a moment. Okay, wherever you are, just think about me when you make money. Otherwise, don't think, really. We cannot help. So, all right, I think this is simple physics. You know what to do with it. You have studied it before in 12th standard. You study it again. Okay. Now, what are the things we are interested in for this class? We are interested in few parameters like, you know, B by H, okay, and this kappa value, right? So that's, I'll go to another equation. So the susceptibility and the magnetic moment. Okay, the susceptibility is related to magnetic moment, and these are the two terms we are interested in. Okay, remember we will be discussing again in the next class, so you study a little bit. If you have any queries, I can come back and discuss again. Now, susceptibility, molar susceptibility, how do you get molar susceptibility? Divided by total mole, right, or Avogadro number. Now, from there on, you get the molar susceptibility and mu. These two are related like that, and you get a equation to calculate magnetic moment, how it equate with the magnetic susceptibility. Now, all we need to care, sorry, we are coming back again. All we need to care for this course, we are mainly trying to see the metal complexes with unpaired electrons, d electrons, right? So, number of unpaired electrons is going to matter to us because the unpaired electrons are the one which are going to give you the magnetic moment. Okay. Of course, we need to worry about high spin and low spin because that will also determine indirectly what is going to be the number of unpaired electrons. And from there, we can of course try to see the spectral behavior and structure of the complex. Now, many transition metal salts and complexes are paramagnetic, of course, due to their partially filled d orbitals. The moment everything gets filled, you don't get much of a magnetic moment. The experimentally measured magnetic moment and of course, the equation I was talking can provide some important information about the compound themselves. So, what we do, we have a compound, we try to measure the magnetic moment, and we have an equation from where we can calculate the magnetic moment. Now, we try to see the difference between the two and try to explain what is the reason if experimental values are differing. Okay? Let me get into it, will be little bit clearer. So, as I was saying, the source of magnetism in the molecule is going to be your unpaired electron. That's all. Now, the unpaired electron can have two sorts of or two sources of creating magnetism. One is spinning around its own axis, and another is while spinning around its own axis, it is also rotating on the along the orbital, right? So two components, the ML or L component, orbital component for which it is rotating around the orbital, and the other component is the spinning around its own axis or along its own axis. Two components. But the d orbitals are the one which are getting affected mostly by the ligand. Metal d orbitals are getting affected by the ligands. So the ligand will not allow too much to spin around its orbital. So the L component, mu orbital component, will be usually minimized, let's say 0. The metal electrons will only be able to give you spin only value, they are spinning, they are not able to freely rotate around its orbital because ligand electrons are overlapping and ligand electrons are restricting them. So essentially what you need to understand is the magnetic or mu total is ending up to be what? Spin only value. But in reality, you have to have the spin only value and the mu orbital value coupled together, or it's a vector addition you can do, and that's what the mu total is going to be. In reality, it is going to be the mu spin only value. Clear? Two components are there, one component will be marginalized. Of course, I am not saying it is 0. Okay? It will come back. That is what we'll be seeing, the orbital contribution. And there is usually 1 or 2 questions are asked from orbital contribution, which is little bit exciting. But usually speaking, two components are there, one is nullified, another is left, that is the spin only. Okay? Now what is the equation over here? This is the mu L plus S, both orbital and spin. This is the equation, this is the correct equation. This is the incorrect or partially true equation, but this is the one which we do care. What is the correct equation? It has total number of unpaired electron and those L values, you have to know all of them. This is the theoretically calculated value. Okay? Now in reality, this is the spin only formula where you get rid of the L value. It is 1 by root over this spin component and L component, right? But if you get rid of that component, it becomes 4s into s plus 1 root of that, right? If you get rid of that component, orbital component. Now s is nothing but number of unpaired electron you are having. Okay? So S equals, total S equals number of unpaired electron divided by 2, or you can convert this equation by putting the number of unpaired electron, it becomes n into n plus 2, n times n plus 2 root of that. Simple. That is what you need to remember. I think you have studied it before. Okay? N multiplied by n plus 2, the root of that. Okay? So if you have one unpaired electron, you know 1 multiplied by 1 plus 2, root of 3, 1.73. 2 unpaired electron, 2 plus 2 multiplied by 2, root of 8, 2.83. So there is an easy way to remember it. 1, 1.73, 2, 2.83. So 1 unpaired electron, 1 plus 0.73. 2 unpaired electron, 2 plus 0.83. 3 unpaired electron, 3 plus 0.8. 4 unpaired electron, 4 plus 0.9. I mean 0.7, let's say. 1.7, 2.7, 3.7, 4.7, and 5.7. It's close. Anyway, that's how you don't have to every time use your calculator. Okay. Now, this is the spin only formula. Now, we need to really get to see now whether the spin only formula is valid always, what we get experimentally when it deviates, how it deviates. Okay, that is what we are going to discuss. These are for the purist. Okay, now we'll discuss when we are going to get something like called orbital contribution. What is orbital contribution? Orbital contribution is nothing but orbital contribution, right? So what is it? Orbital contribution. So in addition to spin only values, if there is some rotation around the orbit, specifically it comes when you have again orbitals which are unsymmetrically filled, like T2G4. So there is some sort of transition from one orbital to other. When you can write down multiple electronic configuration, T2G4, it could be dxy2, dyz1, dxz1, or other way around also. You can, among the three degenerate orbitals, you can write down differently, right? So this is when the orbital contribution comes, because since the electrons can be delocalized or can be placed in different orbital, and thereby you have the possibility of promoting some of the orbital, some sort of movement or some sort of magnetic moment can be generated due to this, you can say the transition, due to this mobilization of electron from one orbital to another, dxy to dyz to dxz. But can you do that? That is what the question. So that's what we want to see. Can we interconvert dxy into dyz or dx2y2 into dyz? That's so the orbital contribution is nothing but spin only value plus something extra you get. Usually speaking, spin only value should be good enough, and our calculated number of unpaired electron should give us the exact value the experiment is going to give us. Often what we see that experimental value are little bit more than number of unpaired electron calculation. How do you calculate number of unpaired electron? That is by your crystal field theory. How many unpaired electrons are there? T2G, EG calculation you do. So number of unpaired electron calculation should give you a very close idea what is going to be your magnetic moment. That is your theoretical calculation. Correct theoretical calculation should include the L plus S orbital moment also, but orbital moment calculation is, or that much value we don't get. The value what experimentally we get is usually close to the spin only value. But on top of that, spin only value itself is not going to be sufficient. Some or very little amount of orbital momentum value comes. When it comes, this is the scenario we are going to discuss. So I will just briefly, I think little bit confusing, maybe I have made it. So there is always L plus S contribution, but I am trying to say you just minimize it to S, but in reality S plus, let's say delta L, very little contribution from L. When this comes, usually you see your experimental data and theoretically predicted data are same. Some cases you have to worry about the orbital angular momentum. When you have to worry about orbital angular momentum. When you can convert one orbital to another, thereby you have the possibility of distributing the electron in different ways, then only you can do that. Now, the degenerate T2G orbital dxy, dxz, dyz can be interconverted as is shown in here. You just rotate little bit, you can interconvert, right? electron in a T2g orbital can contribute to orbital angular momentum. But what happened to Eg? So this is the transition from dxz to dzx to dyz. You just rotate the orbital. It's a plane, dxy plane, let's say. You just rotate 90 degree. You get another one. If it is dxz, you get initial, and then finally you get dyz, right? You should be able to do that. You just take a piece of paper and rotate how much angle you are rotating. You should be able to do. Now, if you look at Eg orbital, you have dz square and dx2y2. Any amount of rotation, is it going to give you the interconversion? No. So Eg orbital cannot give you the cannot contribute for your orbital contribution, right? Now Eg orbital cannot contribute to orbital angular momentum, right? So, but there is a way to convert the Eg into T2g. How it is? dx2y2 or dxy can be converted to dx2y2 and vice versa, right? So there is some way to do that, and then you know that once you get dxy, dxy can be converted into dyz, dxz. So these are kind of interconvertible. So what is not interconvertible orbital wise? So dz square to anything else you cannot do, but rest four of them can be interconverted. Okay. Now orbital contribution to the magnetic moment. Once again, magnetic moment is spin plus orbital contribution should be there. Orbital contribution is usually 0. Orbital contribution can come when it is something like this. Okay. T2g electron arrangement, right? Think of possible T2g electron arrangement. It can be D1. D1 can be organized as is shown dxz, dyz and dxy. Possible T2g arrangement is three different ways you can put the electrons, thereby orbital contribution is yes. D1 in titanium 3 plus. So if you calculate the angular total magnetic moment for these, one electron should give you what? 1.73. It will be little bit more than that. Let's say experimentally found value is 1.83 instead of 1.73. Why it is that? Because it is coming from here. Because see, if it is fixed on an orbital, if it is fixed in this orbital, maybe of course your ligand electrons and these ligand orbital overlap with the d orbitals will be restricting the rotation. Since if there is multiple orientation possible, then that can cause, see, anything that is allowed to rotate, allowed to spin, allowed to rotate will give you some magnetic moment value. You are able to rotate among these orbitals, d orbitals, that should allow you some sort of magnetic moment value. Okay, I think I should give a better explanation. Okay, I'll have to look at that. But that is, I think, the moment you are freezing something, you are not going to get it. If this d orbital is going to overlap with the ligand d orbital, okay, then complete overlap means you are going to restrict the orbital motion. The moment you are giving its multiple possibilities, then you are allowing somewhat to rotate around the orbital, and thereby some contribution is coming. You are not allowing a free rotation, thereby the component will not be huge, but since it can interconvert between or among all these orbitals, it gives you some possibility to give some contribution for the magnetic moment. I think that makes some sense. If it is not 100% clear, I will try to look at more. Okay, I will come back on to the magnetism in the next class as well. Now, in the D2 orbital, as you see, once again, three different ways the electron can be distributed, and therefore these degrees of freedom, as you can see or as you can tell, degrees of freedom should give some sort of magnetic moment value, and that is where you can get the orbital contribution. So the experimental value once again will be little bit more than what we see for the two unpaired electron. Okay? So the spin only plus some value should be there. I think it is not readable from there, but it should be in the slide. So orbital angular momentum, that orbital motion, we are able to see in these cases. Okay? Look at it, I will stop it in here. From here on, I will discuss in the next class.